Very good, very good evening to you, Chris. The Chris VA7 Papa Kilo is a very avid amateur, and which is great. And he gets in on contests, enjoys contests, and is introducing his daughter to amateur radio, which is great. And they're having fun together as father and daughter, which is super. Chris is the firmware and electronics engineering lead, unless that has changed since I chatted with him last
Oh,
time.
that's the same.
Same at Axis. Is that how you pronounce it?
It's pronounced Axis, and it causes no end of confusion. But that's the way it's. I think part of it is Axis because the kind of work that we do, but also you put a Y in it and you can trademark it.
All
Right.
right, good. Anyways, and Axis is located in Sydney, which of course is
Yes.
just up the road from Victoria. A really nice community, and I had a yeah. Anyways, I'll leave it at that. So, welcome, Chris. You're going to tell us about radio, buoys, and marine science, I gather.
Yeah. So hopefully this won't start auto playing on me. If it does, I'll be bouncing it back. Um, but yeah, basically, so what I do, so as Glenn said, I'm the firmware and electronics engineering team lead at Axis. And what we do is we are a buoy manufacturer and integrator. So most of us, when we think of buoys, think of something like this. So that's, one you might moor your boat to on the right there. And then, these navigational buoys that you see on the left. And of course, got a little solar top light on it. And, of course, we've probably seen these sorts of buoys out there too, marking a crab trap or where someone's water intake is for some sort of system. But the kind of buoys that I'm dealing with are things like this. And this is one of the little guys. So these buoys, I kind of think of it as underwater cables in a lot of ways. Most people aren't aware of how many underwater cables there are all over the world. And then you look at a map and you go, my goodness, there's underwater cables everywhere. If you start looking around, you'll start noticing that there are these fairly sophisticated buoys all over the world. And there's lots of them around Victoria. Anybody who's been out around Trial Islands will have seen, well, until recently, would have seen two Axis buoys floating out there. One of them was recently recorded or retrieved, sorry. But we are a global company. We have people working all over the world, but most of us are up in Sydney on a day-to-day basis. And we make these buoys. These are all satellite linked. We do data as a service. So we own a bunch of the buoys that we deploy as a fleet. We sell the buoys to customers all over the world. Particularly hot areas right now are South America and East Asia, but we have buoys everywhere. And they are making measurements of a variety of things in the water and then uploading them via the satellite network to our managed data system. And then we are providing that data to our customers. And these might be private companies who need to support commercial operations. These also could be a lot of time governments. One of the quite popular products we have are these wave buoys. So this buoy is about 1 meter in diameter. It has a inertial measurement system inside of it. You can see it's got a bunch of solar panels. Can people see my pointer on the screen if I
Yes.
move it around?
Yes.
Okay, excellent. So we got an array of solar panels. There's a clear dome here. This whole buoy is sealed, and right there, that is a satellite transmitter. There's an AIS system right here, so this is making sure that the buoy is marked as an obstacle in the ocean, so it doesn't get run over. That doesn't normally stop large vessels from running them over. They get run over all the time, but they survive. And what this buoy is in particular is doing is every 20 minutes, it's taking a bunch of statistics about how it's moving around based on an internal inertial measurement system. And then it's computing a bunch of statistics about the waves that it's experiencing, how high the waves are, what direction they're moving, all sorts of spectral data about waves. And then that is sent to whoever the customer is. So they might be a government in the Caribbean who is concerned about incoming storms, storm surge, things like that. It might be a government or a private entity that's doing construction work and needs to control their construction equipment based on the predictions of incoming wave fronts and whatnot for safety and for stability of whatever they're building. We've also done versions of these that include a GPS system for measuring the height of the buoy. So we can actually do tidal measurements of these, and it's boggles the mind when you think about it. But GPS nowadays is accurate to a centimeter or less if you get what's called a correction service. And these are subscription services that are unfortunately not terribly cheap, but it allows the buoy to quite accurately report its height. And to that degree, we can get very, very accurate tidal predictions. You may have noticed if you go to the shore around Victoria, there'll be these predictions about how high the tide will be. And those predictions tend to be generally terrible on the specifics of it. And so these sorts of buoys go all over the world. We also do a bit bigger buoys. So this is what we call the Watch Keeper. I don't mean for this to be a commercial, but I'm just going to sort of run through the main buoys that we make. And this has got all the same features as the other buoy, wave measurements, things like that. But this also is going to have what's called an ADCP, or an acoustic Doppler current profiler. So this circular area here, this is a moon pool. Some of you may have been on a dive boat before that has a big opening in the middle of the boat where you can jump into the water without actually going over the gunnels. That's called a moon pool. And we will mount sensors in the moon pools on the buoys, and it's a very much similar to how radio direction finding works, but and very similar to how Doppler weather radar works. It's sending acoustic beams down into the water in 3 or more directions, looking at the Doppler shift on backscatter from particles in the water. And based on how long it takes for the echo to get back, it knows how deep it's looking at the various backscatters. And as a result, it can construct a 3D map of currents under the water. And these are, of course, very important for all sorts of global science. And if you're putting piles into the ocean or installing an oil platform or something like that, you need to know what the current is doing. And we can put multiple current sensors on one of these. This also is carrying weather stations. So up here we have an ultrasonic wind gauge, which is measuring very similar to how the current measurement's working. It's actually making these little ultrasonic pings. And as the wind is blowing through it, it's delaying the ping from one transmitter being received by another transmitter. And similarly, by triangulation, you can actually construct which way the wind must be blowing through it. These will also have precipitation meters, barometers, and whatnot. So they're essentially floating weather stations. In a lot of ways, these are set up essentially like satellites. They'll go out and then they won't be recovered for 2 years at a time, and they're completely self-sufficient. These ones and the previous one running entirely on solar power. We'll get into a couple bigger ones in a moment. So there's a big bank of batteries that's down in the bottom, which helps act as the ballast. And then some of my mechanical colleagues, in addition to designing all the superstructure work, also designed the mooring systems, which you'll be forgiven for thinking that they're just fancy ropes. That's what I thought when I first got into the buoy industry. They are massively complicated mooring systems, from anchors on the bottom to shock lines to absorb the heave. And the buoy, of course, trying to keep it in a certain position so that they can take accurate measurements. This buoy also has cellular connection here. It's got the satellite communication as before. This one also has an AIS antenna, which is what this fellow is here. That's a 170 megahertz VHF antenna. And then we can install point-to-point UHF links, where if somebody doesn't want to be running off the cellular network or the satellite network, we can put a dedicated UHF buoy to shore or buoy to station link on there. And that also means that they don't have to necessarily deal with the delays that you might encounter with the satellite network, although those are getting incredibly short these days as well. So this is the big guy. This is the buoy. It looks like an armored boat, but this is actually what we call the Wind Sentinel. It's built around what's called a Nomad hull. This is a U.S. Navy design from around the Second World War. And what this buoy has, as you can see, it's got massive solar panels. They actually have 4 solar panels on them now. There's wind generation in the back of it, and there's 4 watertight compartments in the buoy. In the back of it, there's a diesel generator or sometimes a fuel cell. And the next compartment, there's all your fuel, and then a massive battery bank and a power distribution system. And then in the front, we have industrial PCs running a variety of data capture programs and gathering off of all the sensors. So again, you can see all the meteorological sensors up on the foremast here. If you look closely, you can see a pair of GNSS, which is the generic term for GPS receiver antennas here. So these are actually giving us precise heading, even if the buoy's internal magnetic compass is being confused by the tilt of the buoy. We can do buoy orientation and heave by taking a pair of GPS signals. And then we do all sorts of other things on here. There might be like bird and bat sensors, acoustic um, and radio tags that might be received on here. And so you look at something like this and you wonder what this actually is for. And one of Axis's big businesses is working in the wind farm industry. We don't build wind farms, but if you decide one day that you want to build a wind farm, you're going to discover that you need to take out an awfully large loan from an industrial bank who's going to lend you the money to build your wind farm so that you can not go broke while you're waiting for the wind generation to start. And the first thing that that bank is going to ask you is, how much power do you think you can generate? And that's where something like this comes in. So what you can't see on this one, because it's behind, actually, it's right here, this yellow block here. You can see there's a little opening in the top of it. This is a LiDAR, which is light direction and ranging. So it's the same as radar, but instead of with radio waves, it's done with light. And what this has in it is it sending a laser beam up into the sky, rotating about in a cone. So the beam is tracing a cone. And as the beam whips around, it's looking at backscatter from bits of particulate in the air. And from the backscatter, and then again from the Doppler shift, so it creates a minuscule frequency shift in the reflected light, they are able to compute the wind direction and speed at various heights above the buoy, up to about 300 meters. So this buoy normally actually carries two of these LiDAR systems, and then part of the proprietary technology that the company has developed, and Axis was the first company in the world to do this, is as the buoy is pitching around, it's compensating for all of the pitch and roll of the buoy in those measurements. And so what this buoy is actually trying to replace is a met mast. So that's what this large tower is here. And this was up until about 15 years ago. This was the state of the art for how you survey a site. If you're going to build a wind farm or do any other sort of up into the wind column measurements, you would put a pile down, put a platform on it, and then build a tower. I also look at this and think about all the antennas that I could put on this, but they won't let me do that. And these are basically wind measurement systems up the tower at various heights. These cost several $1,000,000 just to install, let alone operate and maintain. And then, of course, once you've done your survey, you're now stuck with a mast somewhere. You can't exactly move it around. And so that's where these, what we call FLIDAR buoys or wind sentinels, come around. We anchor those in the water on contract or sometimes on spec. Well, the way the world is set up for wind farm production is they have areas out in the water which is called a wind lease. These are owned by the governments of the various jurisdictions, and they then auction these off, pardon me, to various companies who may be interested in building a wind farm or similar infrastructure in that particular area. And so sometimes we will take a buoy and we will put it out in between a pair of wind leases, knowing that we can sell the data afterwards to various interested companies, or we will deploy a buoy like this on spec for a particular customer who has an exact need. And they'll give us a laundry list of, in addition to the wind measurements, of all the other measurements that they want. And of course, things like those underwater current measurements at various depths, those are going to tell them what they need to take into account for the actual construction. Most of the wind turbines you see that are in the water aren't actually anchored to the bottom the way you'd think. It's not a post that's stuck on the bottom. The whole thing is actually a large buoy that's floating and is anchored with 3 anchors to keep it in one place, which is kind of amazing if you think about something being that big actually being a buoy. But of course, those things undergo a tremendous amount of wear and tear, and they need to make sure that they're engineered properly. We'll also put sensors all up and down the mooring lines sometimes. We've put fish tag readers on some of these because they want to check to see if there's active fish migrations going through the area. Environmental concerns are becoming a big aspect of this. We'll put hydrophones on the mooring lines to see if there's whale activity, things like that. So it's from about 300 meters up in the air column down all the way down to the bottom, we're taking what we call met ocean readings of the entire area. So, this is Island HF, and I'm giving you guys all talk about buoys that we work on, and not one of them has had anything HF on it so far. Um, the reason is the essentially low bandwidth, high noise floor. Obviously, the antennas are very, very large. Um, Terrestrial long range can mean that you have platform to platform interference. So if we have multiple buoys out in an area, quite often a fleet of or a whole group of them will go out to take multiple measurements. If they're interfering with each other, that's actually going to be a problem. And so the way I think of it is all the things that make HF fun and interesting for us as radio amateurs actually makes it a real pain to use as a reliable data pipeline. That said, some of the early access wave buoys, that's that spherical one that I showed at the beginning, did use low VHF, so 46.2 megahertz for longer range data comms. And this was before satellite communications was nearly as reliable and as fast and as affordable as it is today. And of course, having the large antenna, just what's essentially a 6.5 or 7 meter band whip antenna, these would act like sails and tip the buoy over quite substantially in the wind, meaning that our solar panels were quite often not facing the sun anymore. And so you'd lose on what we call our power budget. And sometimes if the buoy tipped over, because they can flip right over on their mooring, once it's in the water, if anybody's ever been out fishing and put their fishing rod in the water, trolling, you're familiar with how much resistance that just the fishing rod in the water can offer. The buoy wouldn't right itself anymore because the antenna would just that whip would keep it from flipping around. A wave buoy you tend to want to have as a spherical hull that can move around easily on the waves, and so it's not necessarily as stable as a ship's hull. But we do use some HF. I mean, not Axis personally, but there is a lot of interesting HF work that's going on in the marine sector, marine science sector. And anybody who's out around the coastlines may see one of these things. It looks like a whip antenna with a request service bell attached halfway up it. This is what's called a CODAR wave measurement antenna. And so there'll be a single transmitter and then at least 3, sometimes more receivers that will be spaced up and down the coast. And these run from 4 megahertz to 50 megahertz. And I will see if my link will work here for us while I'm showing my screen. And if not, I'll share it with people afterwards. They're sending out these pulses that are varying in frequency. They're sort of sweeping a frequency. And then the received pulses are coming back. And again, from the Doppler shifts, as the wave is interacting with the currents and the radio waves are interacting with the currents and the waves on the surface of the water, it builds up a map of all of the ocean sea surface currents, which again is pretty amazing when you think about as simple as just a single vertical radiator and a few receivers also with vertical antennas just in known surveyed positions. As you would expect, the low frequency 4 megahertz gives you really, really long range, not as precision of a measurement. And then all the way up to 50 megahertz, you get much shorter range, but you get a much more fine resolution measurement. So let's see if I can actually load one of these, because you may have. Oh hush, skip verification. I know it's safe. Can people still see?
Yep.
Okay. So this hopefully will. Oh no, that's not the one I wanted to play. That's the commercial. Let's go back to the PowerPoint. Try the second one. The second one's should be more interesting. Hopefully the audio comes through. Oh, they're both playing. Let me see if I can skip forward. So this is a commercial from the company that makes them, so apologies.
You don't see them there, Chris.
Oh, you're not seeing it?
No.
Okay. I will share the links with everybody afterwards. So
Yep.
apologies there. There's one link that I've got, which is actually from the company that manufactures these, which gives a fairly broad overview of what they do.
Well, that'd be very useful.
Okay. And then the second link is actually an amateur who did a recording of one. And if you listen around, you may hear one of these. There are CODARs, I believe, in the Victoria area. They're not in the amateur bands. You don't need to worry about interfering, and they're not putting out a ton of power. I think it's on the order of 10 watts. But they are interesting. If you hear one, you'll definitely know it. So this is kind of what you get out of one of these things. So there's transmitting stations and then receiving stations, and it's hard to make out on the map, but each of the stations you're getting these radial lines, and they're giving intensity and Doppler and direction along that line. And then by combining them all, what they actually get is, and this is a zoom in on this area here where you've got good overlap of several stations. You can see these arrows. These are the vectors that are pointing. This is what the currents were doing at that particular moment. And as the tide changes, you can see these systems, the currents in real time. They're also doing this now with X-band radar, which is up in the gigahertz. And it would be the kind of improvement you would expect. You're getting a much, much more fine resolution. It looks almost like video when you see it. You're not seeing these spaced out vectors. You're seeing what looks like a very, very fine resolution video, but showing, you can see wavefronts coming in. And some companies now are using this sort of equipment to schedule when to park the blades on their wind farms, right? So if you have a gust coming in with the wave radar, you can get a few minutes warning that that gust is coming in, and that gives you enough time as a wind farm operator to slow down all of your turbines, rotate the blades, and lock the turbines so that the wind gust can pass through the wind farm. And it can even be accurate enough that you know which wind turbines you need to protect, because maybe it's a localized gust. And so they'll park those for a few minutes and then let them spin up again. And so that will allow the wind farms to operate in much more extreme conditions because they can filter out the actual limiting aspects. And that's kind of all I've got. I kind of thought I'd close with a picture of my daughter and I in contest together. She's going to be 11 in May. Um, it's upside down here, but this is actually a happy frown. She's a little bit unsure of herself, but she's making calls. She made a bunch of contacts. We just took a break recently from the radio science stuff. We're going to dive back into it this summer. I figure if I saturate her too much, I'm going to lose her on this stuff. So, but yeah. So hopefully some of you guys next time where there's a contest, she doesn't know CW yet.
Oh,
I don't know how long that will take, but she definitely likes SSB and she likes making contacts. So hopefully next time, if I'm on the air in a contest, you'll get to talk to Madeline as well.
That'd be great. That'd be great.
And that's it. I'm going to stop sharing unless there are questions, and I can go back to some of the other slides.
now I have a question.
Yeah,
Go for
let's get some questions here, Brian.
Yeah, thank you for that, Chris. You mentioned something about sending signals down from the buoy into
Yes.
the water and
Yes.
using Doppler shift.
Yes.
And I just wondered if you could refresh me again. What are you using the Doppler shift for? And
Right.
what frequency would that transmission be on?
So that's all acoustic, because radio and conducting fluids don't tend to go through each other. So radio is an incredibly good, or any conducting fluid is a great absorber of radio waves. So these are acoustic signals. So there's an array of sonar um, um, transducers,
Yeah.
and they're arranged almost like, if you think about the device being at the apex of a pyramid and the transducers being aligned along the edges of the pyramid, and it will send out pulses, and these could be as low as say 62 kilohertz all the way up now to megahertz acoustically, which is, to think about megahertz and acoustic is something else, but that's the kind of pulses that are being sent out. And it depends on the model. What's happening is that as the beams go out, they're hitting particulate in the water and backscattering. And based on the response you get from each of the 3 or 4 or 5 beams, they're mathematically combining it inside of the device, which is called an ADCP. That's or acoustic Doppler current profiler. And from that, it's measuring the water currents below the buoy.
Yeah.
And so it can measure the direction 3-dimensionally of the current. but also by how long it takes the reflections to come back, it can measure how deep below the buoy the current is. And the lower frequencies, 62 kilohertz, 100 kilohertz, 250 kilohertz, those are for much deeper bodies of water. And then the high frequencies, the 500 or 1,000 or 2,000 kilohertz, those are giving you very, very high resolution, but much shorter range, maybe on the order of 50 to 100 meters maximum.
Okay, thank you. Just
Yep.
if I may make a comment,
Yes.
it reminds me in my very much younger days, I was involved in aircraft navigation systems that used a Doppler radar in the gigahertz region, send signals to the ground, and then use the backscatter to measure the aircraft ground speed and drift.
It's almost
Very
certainly the same
interesting.
principle. Yeah, it's very
Exactly.
much the same principle. Yeah,
Sounds the same thing. Oh, thank you. That was very interesting.
no
Right,
problem.
right.
We don't make those. We purchase those, but we integrate them into the systems.
Okay.
Roger?
Yeah. So following on with Brian, Brian is looking under the water. I want to look above the water. You mentioned LiDAR
Yes.
to come up with looking vertically at the wind profile at various altitudes.
Yes.
And of course, you skimmed over the fact that meanwhile, the buoy is not a nice stable platform. It's bobbing
Yes.
all over the place.
Yes.
And you briefly mentioned fixing that. And I can think of two ways of fixing it. One is to have the LiDAR itself on a 3-axis gimbal with a gyroscope underneath it mechanically.
Right.
And I suspect you're doing it electronically. And if so,
Yes.
how are you doing it? And how are you determining the orientation of the buoy so you know what to subtract?
So there are a variety of industrial suppliers that are making high precision, high frequency inertial measurement units.
Yeah, yeah,
This platform in particular on the screen has 4 ways actually of measuring its orientation. The lidar itself actually has some orientation measuring equipment in it. We don't trust it. We tell the lidar that it's sitting still, and then we do the correction afterwards. So the first one is these GPS antennas give us the heading of the buoy
yeah,
with high precision. Inside of the main compartment, the front compartment of the buoy, you can see the hatch right about there. It's about a 1 yard by 1 yard
mhm,
hatch. Is are a pair of our wave sensors. That's a sensor that we make using a third-party inertial measurement system. And then we also have a precision high-speed inertial measurement unit and compass, which is taking, I believe, at 50 or maybe even faster hertz measurements of the orientation of the buoy. And so we have
yeah,
that. We're taking those measurements. In addition to that, because we have GPS on the buoy, we have precise time synchronization. And so everything on the buoy is synchronized very, very
yeah.
precisely so that when we get the data coming from the LiDAR, we know what the tilt of the buoy was at the
At
time that
that.
those measurements
Okay.
came in. And so we do it mathematically after the fact. You
Okay.
generally don't want anything loose on the buoy. So this is actually a really nice clear ocean. Hurricanes go over these things. Parts of them do get ripped off. There is right there at the back. That's a camera, and there's another one up there, and that's so that we can actually look at the buoy. We can log into the buoy over the satellite network and take a look and see after a bad storm has come through. Are there any pieces missing? I was at a conference last spring down in actually just across the way over in Port Angeles, and
Hmm.
the international buoy workshop, and there was a pair of scientists from Taiwan who were giving a presentation on their hurricane measurement buoys. So these are typhoon buoys. These are large buoys like these, but more circular or cylindrical, I should say, and they have all sorts of meteorological equipment on them, and they would put them out in the known paths of hurricane or typhoons to gather information about those typhoons days before they would actually hit the island of Formosa. And there was a question in the audience which came after their presentation, said, well, how do you protect the sensors from the typhoon? And their answer was, we don't. We just buy new sensors after the typhoon goes through because they don't survive.
Yeah.
They don't survive. Right.
Uh-huh.
So these guys will we've had some of these buoys do full barrel rolls and survive and keep doing measurements. They are fully sealed. If there's any fuel leaks inside of them, nothing ever gets pumped out. So they're not polluting the environment with any fluids that they're putting overboard. And they're meant for really, really abusive environments. But you put the worst storms on Earth, or sometimes a container ship that doesn't want to change course, and they do get parts knocked off them.
Yeah. Well,
Any other questions?
what about the actual radio modules themselves? I assume you're buying these sort of off the shelf and integrating them?
Yeah,
Okay.
we use a combination of iridium systems. So I think most people are familiar with the idea
Yeah.
of iridium phones, which are satellite phones. So iridium is much more than phones. So iridium is a satellite communications company. They maintain a fleet of, I think there's 78 satellites in it, but
Yeah.
I'm sure they're always putting up ones to be redundant, operating across a range of frequencies, usually in the 1 to 2 gigahertz range. And then they sell different modules that get incorporated into radios. And these things are as sort of simple as a phone that you can make a phone call with, or text messaging devices. And then they have what they call short burst data, which is um, data bursts ranging from 200 to 2 kilobytes, something like that. And then you get into what they call the Certus services. So there's Certus 100, Certus 200, Certus 500, Certus 700. And these are varying speeds and bandwidth capabilities of essentially TCP
Yeah.
internet communication. And then on top of that, there are companies like Thales, who you probably have seen on various yachts and whatnot in the harbor. And if
Yeah.
anybody here has a vessel, they may have some Thales equipment. Vessel Link by Thales is another satellite internet service. So there's redundancy on all these systems. All of them carry essentially a satellite Internet of Things transceiver that's been around in some form or another for about 20 years, used in everything from truck shipping to navigation. And the buoy essentially calls home once a day to let us know where it is. That it includes a GPS on that device, and also tells us if the buoy is off of its watch circle, which is the circle within which the buoy should never leave. And if the
Yeah.
buoy is ever outside of its watch circle, a whole bunch of people get automated emails telling them something very bad has happened and they better go recover the buoy before it washes up somewhere it's not supposed to be, because at that point it becomes a menace to navigation. So we have a team that's essentially on call worldwide who can go out and recover these things in an emergency. It doesn't happen very often, but you need to know if you've got a large multi-ton floating obstruction washing around in the ocean. It would be quite a hazard if we didn't have a way of knowing if it was off its circle. You might also be able to see, I should point out here, there's a little X here. And if you actually look at it, it's an X no matter which way you look at it. It's a St. Andrew's cross, and that marks this as a research buoy. So if you ever see a buoy that has an X, a yellow X on one of its masts that you can view from any side, that marks it as a scientific research buoy.
Interesting. I have a question for you, Chris.
Sure.
Data sets.
Yes.
There must be terabytes of information that are being generated by these buoys, right?
Yes.
And, are any of these data sets accessible by the general public for, playing around with large language models and AI and that sort of thing?
There are some publicly available data sets. These are generally ones that are generated by government agencies. So obviously the data that we're generating, it's a private company, and we are,
Right.
that data is the advantage that our customers have. And so we
Yep.
don't share that data around unless they are collecting that data for public distribution. Environment Canada actually has a lot of publicly available data. As long as they continue to exist, NOAA has
Yep.
a lot of public data. The British and the Australians also generate a fair amount of public data, as do a lot of the European, Western European countries and Japan. I'd have to go looking around for it. We generally don't use much of it. Sometimes we'll use it as comparison data for what we're doing, but because we have a fleet of dozens of these things, plus all of our customer systems, which we have the right to through our contracts with them to do processing on some of that data, as long as we don't disclose their data. We have a wealth of data that we can already play with, so we don't typically go looking for it, but it is out there. It is out there if you want to go look. What the search term I would look for is metocean, METOCEAN, all one word.
Yeah, I've got that copied down here actually. What's what satellites are you using? You using Grace, or what satellites are you using to?
So we're using the Iridium constellation.
Okay.
There's the Inmarsat system, and then obviously we're using the various GNSS constellations. So that could be GPS, that could be GLONASS, which is the Russian system. My memory is blanking on the Chinese system, but modern GNSS, which is Global Navigational Satellite System receivers, will typically support all of the constellations. You can tell them to ignore certain constellations if you want, to preferentially lock onto one versus the other. They all operate on the same basic principle, but they're all up there and they're available. I did briefly mention correction services. So when I'm talking about GPS and whatnot, giving centimeter accuracy, that's not something that you see on your phone. If you look on your phone, you see this ring around you that tells you maybe your position is accurate to 3 or 4 meters, something like that. There's 2 ways that we can correct for this. One of them is called RTK, or real-time kinematics. There's a real-time kinematic station in Souk, and the way that works is they have an antenna on a very, very precisely surveyed position, and it's receiving information from GPS telling it where it is. And they say, well, we know where we are. And the GPS error is 3 meters that way. And then it broadcasts to the subscribers who are using that signal, usually within about a 20-kilometer radius around it, saying, all right, whatever GPS tells you, you're actually 5 meters or something in this direction. It's a little bit more complicated than that, but essentially it's giving you a precision datum on those systems. That's somewhat conceptually easy to understand. The other one is what's called PPP, or precise point positioning system. And the same way that when your phone tells you that your position is accurate to 4 meters, well, that's kind of a strange thing if you think about it. If it's telling you where you are, but it also somehow knows how accurately it's able to tell you where you are. And what these precise point positioning systems do is they use known deviations and the intersection of lots of these sorts of measurements to sort of wash out the error. And again, it's a subscription service. They're not cheap. They're like hundreds of dollars a month to access one of these services. But you could be out in the middle of the ocean, far away from shore or any cellular correction station, and know your position accurate to 1 or 2 centimeters, which is, even for somebody who works in it, seems mind-boggling.
Yeah. Roger.
Yeah, looking at this yellow buoy here, you've
Yes.
got lots of sensors, data coming in. You've got data going out via radio, or whatever. Something is running all this. There's an operating system. There's a base computer that's
Yeah.
basically making these measurements and knows when to send things. Are you using like an industrial PC, or is it something homebrew, or is it something else?
We're using a combination. So we have our own proprietary buoy controller, which is,
Okay.
as you might imagine, similarly to a satellite in orbit, your number one constraint is how much power you have available. And Axis has, if not the best, one of the best buoy controller systems out there. It's called the Watchman 500. It's been honed over the years, and we have our own software that we've written for it. And it is turning on the sensors just long enough to get a precision measurement, then turning them off again. On a platform like the Wind Sentinel, which is what we have on the screen here, it's not quite as urgent. But if we go back up to the tri-axis buoy, there's not a lot of power being generated on this thing. We were talking to someone in a conference the other day, and they were talking about how they had a low power, not for buoys, but a low power data acquisition system. And I asked them how low the power was, and they said it was about 12 watts. And I very politely explained, I said, if any of our buoys, except for the biggest one, draw 12 watts, something is very wrong. We're measuring in milliwatts how much power that we're consuming. This actually goes back to the question that Glenn was asking too, about like the terabytes of data. We are not sending all of the data up through the satellite system. that would bankrupt any customer, let alone us. So we are sending a lot of the data on various timescales, sometimes every 10 minutes, sometimes every 30 minutes. Some data changes much more slowly. We only make a measurement every hour. And we're sending quite often the salient features of that data that a customer would want to have in real time. But we're also logging at a much higher rate on board the platform. And so when the platform gets recovered, there is orders of magnitude more information and data that is available that is then delivered to the customer.
Yeah.
Good.
Got a question for you.
Sure.
So you mentioned these all these buoys you manufacture on station, and it's a problem if they drift away. But
Yes.
Doesn't Environment Canada drop drift buoys in the North Pacific and have them drift across towards Long Beach and such?
Yes.
Yeah,
Yes.
it's a different-
Is that,
We
that's still
don't,
going on?
we're not in the unmoored buoy business, but there are companies that do make wave drifting buoys, and there are thousands of them out there, and they almost all get recovered. But these are little. Some of them are. It's almost like the phenomena you will heard of with satellites, like picosats. There are projects now where schools and whatnot are making these buoys to be dropped out, maybe alongside of some other scientific buoys, to take a bunch of measurements. And the modern electronics means that these things can send bits of data back to a satellite to get that back to the owner of the buoy or the manager of the data stream. So there totally are drift buoys, and drift buoys are a very important part of our growing knowledge of ocean systems. We're just not in that business.
I actually ran across one off the West Coast one time and sailed up to it just out of curiosity, and it had a big "Do Not Touch" sticker on it.
Yeah.
Let it drift, and it was yellow like this. But aren't those a shipping hazard? You mentioned like a hazard to commercial shipping.
There are regulations on how large they can be. And I think once they're over a certain size, they're going to have an AIS transceiver on board, at which point they're reporting their position to anybody who's nearby. Even if they're not connected to the network, because it's a real-time VHF transmission, it's telling everybody that that there's an obstacle here to avoid. Now, the big container ships don't care. They are calculating their courses and their rudder movements to such a precision to save on fuel.
Yeah.
They won't turn if one of these buoys drifts into their path. They'll just run it over. But yeah.
Any other questions? Ron, get off mute there if you want to.
Here we go. Yeah, you had mentioned that you had some out by Trial Island, and I'm looking at marine traffic right now. I see 4 AIS in a quadrant out there. And I was wondering, you had mentioned they were out there. What was the purpose of putting them out there?
So one of the reasons of putting them out there, so we've done some work with the University of Victoria. They actually own their own Wind Sentinel that we've helped them refit for things, and we've done other projects with UVic. So one of them is out there with their assistance, but in part it's just to get more and more data. So these things Axis in some form or another has existed for about 50 years. They've been a leader in the wind measurement field since about 2013, 2014, and they've been doing wave buoys in some form or other since about 2000. And they're always getting better. So the more, it's like AI or anything like that, the more data we can get from these platforms, the better. I mentioned that the moorings, as an electrical engineer, I like to joke with my mechanical colleagues that it's just fancy rope. But the dynamics of how the mooring behaves in the water. And it's not just an anchor with a chain running up to the buoy. There will be an anchor with a line running up, and then what's called an inverse catenary, where it will sort of almost do an S bend horizontally in the water and then come up to the buoy. The whole reason being to decouple the motion of the buoy from the line coming up from the anchor. And that's because we don't want the mooring line actually influencing the motion of the buoy. We want the buoy to be free floating as much as possible. Otherwise, it's not going to measure waves very well if it's being held in place by the mooring. So it needs to be able to drift around, stay in place, but also move freely with the waves. So it's quite a complicated system. And we work with some local companies in the Lower Mainland, Vancouver Island area who are developing cutting edge numerical simulation software that's for simulating wave action and moorings in the water and things like that. So we're designing these things and actually looking at the motion of how a mooring works. Is a mooring breaking? Do we need to? It's not like not that terrestrial engineering is easy, but terrestrial engineering, we're still working in a lot of what we tend to call engineered environments, right? So if you're designing a car, you know that you're going to put it on a relatively smooth road that's going to meet some standards if it's going to be sold in a developed country. And so engineers can take for granted that they don't have to make every car the ultimate all-terrain vehicle. You don't have any of those things in the ocean, right? The ocean is completely unconstrained in what might come across your buoy. And so as a result, we're still every day we're learning more and more about what works and what doesn't work. And the more buoys we can put in the water, the more we can learn, the better. Trial Islands happens to be good because it's a fairly well understood area. There's tide gauges nearby. There's Environment Canada weather stations. And so it's a good place to do tests.
Excellent.
Okay, so and the one out there's a UVIC buoy out by Uclolet. I see.
Yep. And if anybody was doing boating off of Sydney, there was I had a new version of one of these fellows out just off of Sydney Harbor for a week in early March, doing some testing of a new system for a customer. So, the other thing too is it's not cheap to put one of these things in the water either, because you're having to have a vessel and a crew. If you're just going for a day out and back, you're talking tens of thousands of dollars. If you're taking a vessel out, many tens to hundreds of kilometers, you're now talking hundreds of thousands to $1 million just to deploy a system. So that's the other thing, is that these need to work. You can't just go out and fetch one and tweak a few wires if it's experiencing problems. So there's lots of redundant systems on board the buoys as well. We can turn various features of them on and off. If something fails, we can shut down power to various subsystems, the same way as they do for satellites.
And finally, for me, Chris, how many people work in the Sydney operation?
That's actually a good question. It's probably easier to say how many people don't and work backwards. I'd probably say there's between 35 and 45 people in Sydney. So if you're wondering where Axis is, if you look at Mills Road and McDonald Drive, we're basically right at the corner of Mills and McDonald Drive. And if you're coming down Mills Road towards that intersection of where it hits McDonald, look out your left window right before you get there, and you'll see our buoy yard. There's usually a few of the big wind sentinels and a few other things sitting out there waiting for shipment or getting customized. And then there's an overflow parking lot on McDonald Drive, just towards the next to the spill response center, and that's our overflow parking lot. But there's usually a few systems in there. They're all the same bright yellow. And then over at Titan Boats, sometimes we have a system stored. But because we have customers all over the world, we have staging areas all over the world where we're storing buoys, where we know customers are going to have a need coming up in the future. Usually, like I said, the larger systems will go out for a year and a half, 2 years, 3 years at a time, and they're for very, very large industrial operations. So they know like a year or two ahead of time that they're going to need this equipment, so we can stage it efficiently, rather than to race around the world to get it set up.
Do you do manufacturing in Sydney, Chris?
Yep. We don't manufacture the hulls. So this is, the yellow buoy hull here. It's made to our specifications. We don't do the manufacture of that. We are assembling the solar panels into their frames and arrays. We get our circuit boards made we're an ISO company, and we work with ISO companies to actually get our circuit boards made, but they're made to our specifications. But we are assembling, unfortunately, I can't share any photos of it because it's proprietary, but inside of our control boxes, all of the wiring, the way the components are all being put together and whatnot. So we are doing the buoy integration and manufacturing in terms of putting a completed buoy together in Sydney. Where it's not just an engineering, like an office where we're doing engineering on a computer, where I'm usually running up and downstairs to talk to our production team to make sure that they understand the process, and if they're seeing problems in something I've designed or one of my team has designed, we have a really, really good communication with it all in the same building. It makes it pretty efficient.
Oh, it's fabulous.
Made in Canada too, so it's something we talk about more these days. But it's nice to be at a company that's doing that, and not just Axis, but this part of the world, the Lower Mainland and South and East Vancouver Island, is really a hub of cutting edge marine high tech. Before I was here, I was up in Nanaimo designing remotely controlled miniature submarines. So that kind of tech and expertise is all over this part of the world. So we should be pretty proud of it.
So is your office near Terra Remote Sensing? I'm just looking at Earth Google.
I'm gonna look where that is because I'm not sure where that is.
Because you mentioned the intersection of Mills Road and McDonald, right?
Yeah. That's Terra. How's that spelled?
Terra, right next to the Sydney Animal Hospital.
Oh yes, they're next to our warehouse. So if you're looking if you're looking on Google Maps right now, go kitty corner across the intersection, and you're probably going to see that there's a place called Pizza Plus, which is the little lunch counter. Right behind Pizza Plus.
Oh, there's Axis. I got it.
Yeah.
Got it.
And if you actually go to your satellite map, you can actually see the yard that has all of our yellow buoys in it.
Oh, that's what that yellow is there. Got it.
Yes, if you're using marked Axis roof, that's what we affectionately call the castle. That's the top of our building, and we usually do GPS tests up there. And it's unobstructed solar power for testing solar systems.
Right. Hey, we're coming up to 8 o'clock, gentlemen.
I'll hand it back to you guys.
I'm just going to one more query as to anybody who has a question. Okay, Chris, this has been totally fascinating.
I'm sorry there wasn't more HF.
No, you don't have to apologize for that.